Okay, so now what we're going to do is we're going to evaluate these expressions, and as you can see, it says to do it without a calculator here. And so sometimes we will have to use a calculator, but on these we shouldn't have to, and you're expected not to. So remember from the previous video, so you can convert the to exponential form. What we can do is, I know it's not an equation, but what we can do is basically say, okay, I'm trying to figure out what this is equal to. And so remember, really, logs, you don't want to overthink it. A lot of times we get kind of scared because we see a word, log, right? But really, just think that that's representing you're trying to find an exponent. You're trying to find an unknown power. And so what this is, this would be rewritten as 4 to what power gives you 16? Well, that power would have to be 2. And so that's the answer to part A right there. So B is going to be the same thing. You're trying to figure out what power would be required to turn this into 27. So 3 to what power equals 27? Well, that would be 3, right? 3 to the power of 3 is 27. And they'll get a little bit more complicated than this, but the next one shouldn't be too bad. So looking at example C, what we're doing here is 6 to what power would give you 1? Okay, so if you remember your rules of properties of exponents, that's going to be 0. So any number raised to the power of 0 will equal 1 as long as that number is not 0 itself, as long as the base is not 0. That we won't do a base of 0 at any point, so you don't really have to worry about that. So then now we're going to get a little more interesting here. So 3 to what power would give us 1/3? So once again, you have to recall your properties of exponents. And so somehow, basically, this kind of became the reciprocal, right? It got flipped, right? It got flipped. And so negative exponents are what are going to cause a flip. And so the answer is -1, because if you have 3 to the power of -1, you have to take the reciprocal, and then that becomes a +1, which then gives you 1/3. All right. So looking at E, kind of the same idea. So 2 to what power would give us 1/8? Let's see. Well, 2 to the power of 3 would give me 8, but I want 1/8. So I need a reciprocal also. So the answer to this one's going to be -3. Okay? Because if you take 2 to the -3 power, you're going to have to reciprocate that in order for that exponent to become +3. And then 2 to the power of 3 is 8. So then it's 1/8. So my answer is -3 on example E. On F, this is interesting. So I'm going to have 7 to what power would give me the square root of 7? Well, you're going to have to recall from when we converted, when we had rational exponents and convert them to radicals. And so, for example, if you had, let's say, a base raised to a power of m over n, a power of m divided by n, the denominator will tell you the root that you're taking, and the numerator is going to be the power. It could be on the outside or inside, it doesn't really matter. And so that's kind of what's going on here. And so if you look at this example right here, it's the square root, so it has an understood index of 2, and then we have an understood power of 1 right here. So this would be equivalent to 7 to the power of 1/2 if I convert it from radical form right here into exponential form where my exponent is a fraction. And so 7 to what power would give me 7 to the power of 1/2? Well, that unknown power has to match right there. So my answer would be 1/2 right there. Okay, so a lot of prior knowledge that we're having to pull out here. Let's look at G. So right here, we're going to have 25 to what power would give me 5? Hmm. Well, let's see. How am I going to shrink down like that? So a lot of times students will think it's like a negative value, but negatives will cause you to reciprocate and cause your number to be smaller. But that if I do that, that would actually be 1 over 25, right? If I had a -1 right there. So that's not going to work. What I notice is that if I were to square root 25, that would equal 5, right? So this actually kind of relates to the one we just got done doing. That's going to be 1/2 right there, because 25 raised to the 1/2 power is equivalent to the square root of 25, which we just showed equals 5. So the answer to this one's going to be 1/2 right there. Okay, and then our last example here, H, is going to kind of be a combination of G and some of the other ones here, because we're going to try to figure out how does 1/6 to what power would turn into 36. Well, that's interesting. Well, I kind of need this to reciprocate and become just a 6, right? And so that would be a -1 exponent, but I want it to be 36, not just 6, right? So in order to do that, let's see, what would I have to do? I guess it'd have to be a -2, it looks like. And I believe that's going to be the answer, and we can check it in just a second. So I believe it's going to be -2, because if I take 1/6 to the -2 power, that would flip into 6 squared, which then would be 36 right there. So the answer is -2. -2 is the exponent that would cause that chain reaction right there. Okay, so moving on. Okay, so this is going to be kind of more of the same, and some of these we've actually already seen. So right here, this is just some kind of shortcuts that you'll kind of notice and pick up on. So if the base matches what you're trying to get to, well, yeah, it's going to simplify into a 1, because b to the power of 1, that's going to be the identity exponent power. It gives you right back where you were, right? So b to the power of 1 would give me that b right here. And then right here, if we have a base, it could be, whatever, as long as it's positive, right? And so if my result, I'm looking to get a 1, well, then this is going to be 0 right here, because b to the power of 0 equals 1. So b to the power of 0 equals what's right here. So just remember, that's going to be very crucial that we understand that pattern. Base to power equals. So base to power equals this, right? Base to power gives us this. Okay, then here, same idea. So base to the power of x would give us that base raised to that power of x, right? Base to the power of x gives us what's right here. Now, this last one is a little bit harder to kind of wrap your head around, but right here, if you have a base raised to a power where it's the log of the same base, well, those kind of cancel each other out, and you end up with just that x right there. And I'll kind of show you an example of that when we get there, of kind of why that occurs. But these first couple right here are pretty simple, because right here you're basically asking 4 to what power would give you a 4, right? 4 to the power of 1 would give you a 4, right? 4 to the power of 1 gives you a 4. And then right here, 3 to what power would give you a 1? 3 to the power of 0 would give you a 1 right there. 3 to the power of 0 equals 1, right? Then here, so you're trying to figure out 6 to what power gives you 6 to the power of 8. 6 to what power will give you 6 to the power of 8? Well, to make these two equal, the question mark would have to match the other power, which is 8, right? So it's just 8 right there. Don't overthink it. Now, D is the one that right here, the simple answer is it's just going to be 19, right? That's the answer. It's going to be 19. But if you were trying to do your conversions, I'll show you how that would work. So let's just say we don't know what this equals. We'll just set it equal to y. And so if you remember our conversion, let me go ahead and grab that and I'll pull it up, and then you can kind of see. Okay, so what I currently have is the right-hand side of this right here. So let's make this a little bit easier. Let's change that to an X then, just so we can kind of match what we have written here. Okay, so see, this would be my base right here. That's my base. And then this is my Y value right here. And then last, I've got my X right here. And so if I'm going to convert it to the log format over here, the y, which is the exponent, goes first, right? That's going to go right there. So I'm going to have log base 8 of 19. So that's the y part right here, and then equals, and then log is part of the conversion. That word log just shows up as part of my conversion right there. And then the b right here, the b is this part of it right here, the 8. So that's going to be base 8. And then the x, which is right here, will be that part right there. So it'll just be an x. So then when you look at this, the only way that these two could be equal to each other is if that x right there were also 19. And that's why the answer is 19 right there. Now, do I expect you to do that on these examples? No. I expect you to follow the shortcut. So if you have a base raised to a power of log of that same base, whatever that log is evaluating, that is what it's going to simplify into right there. So that's the way I expect and want you to do it. But I wanted to give you kind of a detailed explanation in case you were curious. Okay, so the next part we're going to look at is our common logs and our natural log functions. So logarithmic functions with base 10 is called the common log. The function right here, f of x equals log base 10 of x, is usually expressed without the base listed there. So a lot of times, because it's the most common one, typically we'll just, so we don't have to write it over and over again, we don't write it because it's just understood. So if you don't see a base listed there, it's just going to be understood as 10. And that's actually what your calculator is going to be defaulted to when you press the log button. Now, some of these newer, fancier calculators, you might be able to adjust your base, but on some of these older ones, like the one I have right up here on the screen, so when I push log right here, that's gonna, has an understood base 10 right now. Then we have another one that is going to be our natural log. So remember when we were using base e for our exponential functions? Well, we also have base e for when we're doing our logarithm functions. And so you could write it as log base e, but we actually do have a shortcut, and it's right here. It's ln. Okay, so not an I. Some people think it's a capital I, but actually it's a lowercase l and a lowercase n. So ln, and that would substitute in for having to put out log base e. And then we have that button in our calculator. In our calculator, they use capital letters, which is fine. Let's see, let me pull that up for you. And that's just right below our log button right there. So LN, which stands for natural log. Okay, so we're going to do a couple of these, and you really don't need a calculator for these. By using the rules that we have up here, we should be okay, these properties. So if you look right here, I haven't understood base 10. I haven't understood base 10, and so you're trying to figure out 10 to what power gives me 10 to the power of 7. 10 to what power gives me 10 to the power of 7? Well, that would mean that my unknown exponent would have to be 7. Okay, here's the rule that I don't think too much about right here. So if you have a base raised to a log of the same base, then it just simplifies into what the logarithm is evaluating. So this is just going to be 33 right there. Okay, then it looks like we have a natural log one. And so this is base e, just so you know. So we're trying to figure out e to what power gives me 1. E to what power gives me 1. Okay, well, e is 2.7 so we know that it's not 0. As long as my base is not 0 and I'm raised to what power would give me 1, it would have to be 0. It'd have to be a 0 right there. All right. And so then our next one, let's see. So E, remember it has an understood base of E. So E to what power gives me E to the power of 6. So E to what power gives me E to the power of 6. And so you can see that right there, that unknown exponent, what I'm looking for, is going to be 6. Okay, so our next one, let's see, this is going to be kind of interesting with what we got going on here. So I know I have a base 10. If I could maybe manipulate this into a base 10 also, that would probably be pretty helpful. And so what I'm going to do here is we can convert that 100 into a 10 squared. So that's what I'm going to do. So we're going to have log, it's understood base 10 of the 5th root of 10 squared. And then what we're going to do is convert this into exponent form right here. And so if we look back here, I have the formula right here. So the index of your root is going to be your denominator, and the exponent, it could be inside or outside, is going to be the numerator. So when I convert this, this is going to convert to log of 10 raised to the power of 2/5. 2/5. And then now, since the base matches what I'm evaluating the base of, then it just simplifies into that exponent right there. So let me review that with y'all right up here. So if you look right here, if if the if the bases match right here on the right side over here, if the bases match, you're just going to simplify into what that exponent power is. So that's what's going to happen here. This is just going to simplify into 2/5. And that's the answer for that one. All right, so same thing kind of with F. We're going to kind of play around with this because I have a natural log, which is base E. So if I could somehow manipulate this into a base E, that would be really helpful. And so what I'm going to do is I'm going to take the reciprocal of this, and so this will become e to the power of -3. And now the base of my log and what I'm evaluating match. So it's just going to simplify into what that power is right there, which is going to be -3. And that's the answer. Okay, and on example G, this is going to be one of those that, once again, try not to overthink it. You have a base E raised to a natural log, which is base E, so it simplifies into what's being evaluated, which is going to be the square root of 7x. That is the answer right there. And then for our last one, H, it's going to kind of be like E. It'll be a little bit easier, but basically you're going to try to figure out how can I condense this into 10 to some power, right? Have a base 10. Well, what we're going to do here is 10. Every time you multiply by 10, that adds a 0. So let's see. Here's 10. So if I want to add 3 zeros, let's see if I were to raise it to the power of 3. I believe that would do it, right? 10 times 10 is 100. Times 10 again would be 1,000. Times 10 again would give us 10,000 right there. Oops, wait, I'm missing a 0. Hold on. There we go. That's better. So let's see. 10 times 10 is 100, then times 10 is 1,000, then times 10 again would give us the 10,000. There we go. So you just have to count the number of zeros. So sorry, I accidentally underlined. There we go. So 1, there we go. All right, so then right here, so our bases match. So it's just going to simplify into that 4 right there. Okay, on these next couple, we're actually going to use the calculator now, and we're going to round 3 decimal places. But I do like us to kind of think about this. So we know it's a base 10, right? And so we're trying to figure out 10 to what power, right? 10 to what power will give us 564. And this is a popular SAT question where they'll give you the answer choices 1, 2, like what's the number between 1 and, I'm sorry, yeah, write that a little bit neater. So the answer is definitely going to be a decimal. Is it between 1 and 2, 2 and 3, 3 and 4, or 4 and 5? And so this will be like a multiple choice question, right? Well, think about this. Um, 10 squared is 100, so it's got to be more than 2, right? And then 10 to the power of 3 would be 1,000, right? So it'd have to be this. My answer's got to be somewhere between 2 and 3, because 10 squared is 100, but 10 to the power of 3 is 1,000. So the first one's not enough. The second one's too much. So I'm going to be wedged somewhere between 2 and 3. And so this is where the calculator is going to come in and help us. And so here we are. So let's see, we're going to do log. So I type in log, it's an understood base 10. And then I'm going to put 564. And let's see what we get, 2.751. So 2.751. And so we rounded 3 decimal places right there. And if I want, I could put that in the calculator and we can see how close that is. So I can do 10 raised to the power of 2.751. And it gets me pretty close. Not exact, but I'm pretty close. But the more decimal places I add, the closer I'm going to get to 564. All right, let's look at B. So this time I'm taking the log of 0.543. And so that's kind of interesting because I'm trying to figure out 10 to what power. And that's actually shrinking, right? So, that could make my exponent maybe a decimal or maybe even negative. Let's see. Let's find out. So we're going to do the log of 0.543. So I got negative 0.265. All right, so that was kind of interesting. And so that happened in the negative and decimal because I shrunk down pretty small. I got less than 1. So that negative and decimal kind of played that role. Okay, so let's look at C. This one's kind of interesting. So 10 to what power would give me negative 6? Hmm. Hmm. 10 to what power would give me negative 6? Well, let's think about this. Well, if I have a negative exponent, it doesn't make my answer negative. It just causes a reciprocal of my base. If I do a decimal, that doesn't make it negative either. So this is actually impossible. And I'm actually going to go ahead and put it in the calculator so you can see what it says. So let's see, log of negative 6. Non-real. Okay, so we don't have an answer for this. Got error. Okay, so what that's going to do for us here is that's going to go back to our definition that when we have a log base, whatever you're evaluating has to be greater than 0. It can't be 0, it's got to be greater than 0. And so no negatives and can't have 0 there. And so this one we're just going to have does not exist. All right, so I got one more here where we're going to do the natural log. And so the difference is it's a base e. So e to what power is going to give us 250. So if you remember, e is around 2.7, so kind of close to 3. So our answer is probably going to be around 4 or 5, something like that. Let's go ahead and plug that in the calculator and see what we get. So this time, you want to use the LN button right here. And then let's see, 250. So 5.521. So 5.521 is what we get there. All right, cool. Well, what if we want to evaluate a log that's not our common log or our natural log? Well, we have this change of base formula right here. So what we're going to do here is whenever you have one of these where the base is not something that's going to be base 10 or base E, what you can do is take the log of what's being evaluated divided by the log of the base and then um, use the same base for that log. So basically you have two options. You can either take the common log or you can take the, oops, should be B right there, or you can take the natural log of those values. And it doesn't matter, but you have to stick with whichever one you choose. So if I choose, for example, here, if I choose log of 100 on top, then on bottom I have to do log of 4. So that's all you're doing here. This goes here, this goes here. You could also, if you wanted to, you could have done natural log of 100 over natural log of 4. Okay, so either one's going to be fine. So before we put it in the calculator, though, let's think, what is our answer going to be close to? So 4 to what power equals 100? Well, we know that 4 squared is 16. 4 to the power of 3 is 64. And then 4 to the power of 4 is going to be 256, right? So we're probably going to be around 3 point something, like maybe 3.2, something like that. So let's go ahead and put this in our calculator and see what we get. So it doesn't matter which one I type in. So I'll just go with the natural log. So natural log of 100, and make sure you close that parentheses, divided by the natural log of 4. And let's see what we got. So 3.322. So I am going to have to round that third decimal place, or it says 4 decimal places here. Okay. So 3.3219. So here we go. 3.3219. There we are. Kind of cool, right? So 4 to that power will give you 100. Okay, so let's look at example B. Same thing. Basically, it's kind of interesting because I'm using 0.41, but take log or natural log. It doesn't really matter. I think most people like to do natural log. So natural log of 0.41 divided by the natural log of 8. And we'll stick that in our calculator and see what we get. So let's see, the natural log of 0.41 divided by the natural log of 8. So we get negative 0.4288. So I had to round that fourth decimal place up because of that 6 right there. That 6 caused me to round that 7 to an 8 right there. Okay, so the last thing we need to talk about, I kind of already addressed this up here, that when we evaluate a logarithm, whatever you're evaluating here has to be greater than 0. Okay, and this is going to kind of lead us into the next video in a moment. But what we're going to do here is find the domain of each logarithm function. Hint, logarithms can only be evaluated at positive values. Therefore, the domain of, and I basically have a basic one written here, but basically my x value has to be greater than 0. So what we're going to do here is I have x plus 4 here. That needs to be greater than 0. So you're just going to take that, solve that, and that will be the domain for this function right here. We're not really so concerned about the base right here. Um, the base has its own rules also, but we're not really going to worry about that right now. We're just worried about this part inside the parentheses. Whatever is being evaluated has to be greater than 0. So then you just solve this, and that will be the domain for this first one, example A. So all my values that I plug in for x have to be greater than 4. So my domain would be from negative 4 to infinity. Just like that. Okay, and example B is kind of the same, except the algebra is a little bit more challenging, but not too bad. So that expression inside here has to be greater than 0. So then you just solve that expression. So we'll subtract by 3 on both sides. And then we'll go ahead and divide by -2. By the way, I meant inequality, not expression. And because what's going to be different about here is when I divide by a negative, I have to reverse the sign, the direction of my inequality. And so this will become x is less than, those double negatives will cancel out, and it should be positive 3 over 2. So all my x values need to be less than 3 halves. So my domain on this one, because of that negative inside there and causing my inequality to reverse direction, I'm actually going to be from negative infinity to 3 halves right there. And so that will be my domain. So that'll be important in the next video, because we're going to graph these starting in the next video. And they're not really going to be that difficult, but it's going to be important to find that domain. It's going to be helpful in terms of being able to graph it. So that's where we'll pick up in the next video.